Welcome to Chemistry Crash. Okay, what I'm going to do is I'm going to use as many examples, but there is more theory in this side of the work, but I've going to try and use as many examples as possible and work through these through the sections with, as I say, perhaps a bit more theory than we did in the physics side of the syllabus. So let's just start off with the first one, and the first one has basically given, and it's the classic graph, okay, where they show you, and it's the one where they show you the melting point, okay, boiling point rather, and it's a graph that sort of looks like this over there, okay, whoops, and here I think they've given the period, 3, 4, etc., etc. And what they've got is they've got here the boiling points, and generally you've got water up there, and you've got some anomalies that start occurring, right? They're saying, for example, the anomaly of CH4 versus H2O boiling points, okay? Or H2S, HCl, pH3, H2O, in all of them, right? So what you've got is you've got this anomaly, generally speaking, and there's one sort of down there, right? Now, on the graph itself, how do we approach these? Well, essentially, what is it about? It's actually about finding out if we can get a hydrogen bond to form or not. Because what causes water to be high up on that scale there is essentially, what have we got? We have got here, we've got the H, the O, like that, and an H. But because this is a polar molecule, which you know, okay, this side is negative, this side is positive, right? What does that mean? It means that on this side here, we could in fact, because it's negative, we could attract another H down over there because that is positive, and between those two over there, we get the hydrogen bond, okay? Which is a strong intermolecular force, right? Now, in water we get it. So we're going to start off with the electronegativities, okay? That's where we're going to, that's our first port of call. So, following it here, we say, okay, CH4 and H2O. So if we look at CH4, what have we got? We have got this molecule over here, like that, okay? Right? So we've got that molecule. Now, in these, we only look at one side of the molecule, the C and the H side. We don't look at all of them, we just look at one. So let us take the electronegativity of carbon is equal to 2.5, okay, and the electronegativity of hydrogen is equal to 2.1. The delta electronegativity, the change, is going to be 0.4. That basically puts us almost covalent, okay, very, very weakly polar, doesn't it? Okay, so essentially in this one, it is very weak. So the hydrogen bonds that form, okay, very, very weak indeed. It hardly happens. Whereas with water, we've got H, O, H like that. And once again, we look at this bond. Electronegativity of oxygen is going to be 3.5. Electronegativity, that's our oxygen. Electronegativity hydrogen, 2.1. The difference, 1.4. Delta electronegativity. This is distinctly polar, right? And what happens is we've got the negative side there and the positive side there, okay? And for those who want a little bit more about it, essentially what we're saying is we're saying that in a covalent molecule, normally they are the same molecule, the electrons between the two are happily shared. So half of the time the electrons are there, the other half of the time they're there. So there's neither one of those atoms is taking more of the electron's time than the other one, because that's really what it's about. If you remember back your ionic bond, okay, your ionic bond was basically where, for example, sodium fluoride, okay, what happened there was the fluorine took this one's electron, left that as positive, and it was minus, which means the electron never goes over to the sodium again. It sits around there like that. So you can see the difference there, Na and fluorine. Electrons there, here, perfectly shared. Okay, so that's basically pure covalent. This over here, ionic. Okay, now as an ionic bond, it means the electron is gone. Okay, sodium doesn't see it, so this side is basically a +1, this side is a -1. Okay, but when they go into water, they dissociate in water, giving us the sodium ion and the fluorine ion, right? Whereas over these guys here, right, the electron shared there, it doesn't form an ion when it goes into a solution situation. Okay, it can, depending on what it's from. Okay, let's have a look at the next bit. Okay, they say, all right, then look at they say look at the anomalies. Okay, for example, H2S and H2O. Once again, you're going to take the change in electronegativities, and you're going to find out that H2S is weakly polar. Okay, whereas we've got the hydrogen bond on water. So that's explaining why, and it's just go back to, well, just redraw it here. Okay, the boiling point here, okay, of the water is high, whereas the H2S was low, right? And then it goes up a bit like that, but it's very low in comparison. Why? Is because we've got hydrogen bonds formed over there, and the hydrogen bond is a strong energy bond. Therefore, in order for us to take the molecules apart to form, well, what are we doing? We are going from a liquid over here to a gaseous state there, which means we need to remove that bond between the and there. Okay, we need to remove that bond. That's a positive, so we're going to get an O coming in there, okay, with an H and an H. This is the bond we're talking about. That's the one we've got to break, and that bond is strong, so therefore we need to put in a lot of energy to break that bond so that we can actually get an atom, a molecule, actually leaving the surface of the water. Okay, right, now let's have a look. The next one is with ammonia and pH3. Okay, so we've got NH3 and pH3. Okay, now if you look at the periodic table, you will see that ammonia and phosphorus are right above, in the same line, aren't they? In other words, yes, nitrogen in its second orbital structure has got a valency of -3. So nitrogen looks like this, okay, with -3 means it's got, which means that it's got 3 parking spaces for electron there. P has got the same structure, but in the fourth, because it's in level 1, level 2, level 3 rather. In the third level, it's got the same structure, okay? That's essentially what, so what we're trying to do is we're trying to explain why the boiling points of nitrogen, okay, and the phosphorus are different, okay, the ammonia and the phosphorus compound. Why are they different? And it comes down to the fact that the ammonia, if we look at it, let's have a look at electronegativity of nitrogen is going to be equal to, let's have a look. Nitrogen is going to be equal to 3 and 2.1 is my hydrogen. Okay, 3 and 2.1. So I've got 0.9. Okay, so over here I've got the polar molecule, polar covalent, so I'm going to get hydrogen bonding forming, whereas for pH3 the electronegativity of phosphor is going to be equal to 2.1, and the electronegativity of hydrogen also equal to 2.1. The difference is equal to 0. Okay, so what have we got here? We have got a 0. Essentially, this molecule, all right, with the hydrogens coming in over there, okay, it's an equal sharing situation, right? Why? Well, because there's no difference in electronegativity. So this is almost pure covalent. What is pure covalent? Sharing of the electrons. So in other words, the electron is going to be evenly distributed. Okay? Now let's take a look and say, okay, in other words, all of these problems are the same. They are the same, right? What we look at is we look at the difference in electronegativity between the two atoms concerned, and that tells us what kind of bond is going to take place between them, right? And depending on what type of bond, if it's got a hydrogen in it, okay, then we would look and see if it's polar, therefore we've got a plus and a minus side, which means we can get a bond between the two, right? Let us, for example, have a look at let's have a look at boron and fluorine, okay, shall we? With regard to the molecular shapes, etc., and things like that. Let's just look at boron. Now, boron is, let's count it, 1, 2, 3, 4. It's number 5. So boron is element 5, okay, which means it has got 5 electrons, which means we can work out its structure: 1s2, 2s2, and 2p1. Okay. Now, when we draw the Lewis diagrams of these, remember we only do the outer shell. So therefore, we have got boron sitting over there. What is special here is we say, let's have a look at what it looks like. Let's draw it. So we're going to have to draw 1, 2, 3. Okay. So boron effectively has got 3 parking spaces, hasn't it? Now along comes fluorine, for example, or chlorine or whatever, and we can put fluorine in there, and fluorine in there, and a fluorine in there. Right? Now they want to know what shape is that molecule. Well, let us look at it spatially. First of all, we say, right, can you see that on this side here, and this is the key to it, is to say there's no other electron pairs on that side. Okay? In other words, it's vacant space. Okay? So what can happen here is that when the fluorine comes in and joins with its electron, okay, what have we got? We have got the boron sitting in the middle and these guys coming in and joining there. So what do? Well, they want to be as far apart as each other. So let's look at it like this. We've got boron sitting over here. Let's pretend it's a spherical surface like this, and we're looking down on it. What happens? The boron is there. These guys, now this is an electron and that's an electron there that's sharing an orbital, right? But there's electrons as well. These guys, from a space point of view, okay, they kind of don't want to be as close as possible. So they're going to try and get as far apart as possible, aren't they? Right? Because this is a negative here, and this is a negative, and this is a negative. So they are going to, looking at your side, they are going to orient themselves around the molecule. So they're going to try and occupy the space so they can be as far apart from each other as possible. But in this case, it's all in one plane, isn't it? They don't need to go to a different dimension because they're happy like this. Can you see that each one can distribute it evenly around? Okay? So what happens here is that in this situation, this boron trifluoride is going to be a molecule which is flat, and anything that's flat is on a plane, and it's got 3 legs, so it's called trigonal planar, right? Because it's got the 3 sort of like a poiky, hasn't it? 3 on equalizing in the space, right? Now let's look let's go back and look at ammonia, shall we? Just out of interest, and see what would ammonia be like, and let's look at the difference, okay? Okay, so trigonal planar would be that one. Let's now look at ammonia, NH3. Okay, there's our N. Now, we said N is 1, 2, 3, 1, 2, 3, 4, 5, 6. N has got 7 electrons. Okay, so therefore, that is 1s2, 2s2, that's 4, 2p3. Once again, we draw these guys on the outside, so we can draw N like this. 1, 2, 3, 4, 5. We have 5, so we've got a valency of -3, but we've got 3 parking spots for electrons, haven't we? So what have we got over here? We've got the 3 that can come in. Now, let's go back to our old faithful ammonia, and you'll see in the next section we're going to use ammonia a lot. Look at the difference here. The difference between them is this. Previously, remember, the boron, okay, I'll go back to green, the boron had no electrons on that side. Okay, there's nothing there, it's empty space. So these lobes, the orbits can move out. But now what happens with ammonia is, and this is the big difference, is this. Can you see that we've got 2 electrons there? That is our lone pair. Right? So what is happening? It means that now the hydrogen, the ammonia links with 3 hydrogens, because in the second level energy state, that's the only parking spots that are available. So 3 hydrogens come into it, okay? Assuming we are synthesizing ammonia. Now what happens here? Well, here we've got a lone pair of electrons on that side, haven't we? Right? Now, if we were on a plane like this, then they would occupy that space, wouldn't they? They would also occupy on a plane. But it's not a plane. The molecule, or the atom, then is round, okay? So what can happen now is we say, right, the one can sit here, if it was all in a plane, there, and there, correct? But now we've got a 3-dimensional surface. So these things can now say, okay, well, I'm going to move around a bit, right, on that surface. So what do we find? We find that they want to get as far away from each other as possible on a sphere, okay? And if you look at a sphere, take any ball that you've got and look at it and try and work out how you can arrange 3 vertical toothpicks into there, that they are all as far apart as possible. And you will find that what they form is they form a molecule where the nitrogen sits over, okay, that's not a, it's a little, I didn't want to use don't want to use green, use the black again so that we can see it. Let's just move it up slightly. The nitrogen sits in the middle over here, right? And it's a 3-dimension. So what happens is one guy stands above, another one sort of goes on the back over there, another one over there, and another one. So you get this kind of tripod structure, because down at the bottom, remember, this is the lone pair here, right? That's the lone pair. They sit on top. The other 2 get pushed down away from the lone pair. So essentially, you form a tripod, don't you, of your hydrogens here and the lone pair of electrons there. Okay? Now, that is 3 again, so it's trigonal, okay? But it's pyramidal, okay? So now we've got that situation. This lone pair, however, right, because you've got an H down here and an H down here, remember what we said about the difference in electronegativity. We said the difference in electronegativity between them was essentially nitrogen was 0.9, okay? Okay, so it's 0.9. So what actually happens here is that this side here, these electrons here are permanent. So hypothetically, okay, just conceptually, all right? All right. This has got 2 electrons, so let's say that's got a charge of -2. Okay? Just in order to explain it. Okay, it's -2. What happens down here? Well, we've also got 2 electrons, so there's the electron -1 from the nitrogen. But we've also got an electron from this guy, haven't we? The hydrogen sharing one, right? But what is happening here is this electron is with the nitrogen. These 2 are with the nitrogen, right? The ones that are with the hydrogens over here, like that, those guys there, if you look at the difference in electronegativity of 0.9, what is it saying? It's saying that on that leg there, let's draw it, nitrogen and hydrogen. On this leg here, this black electron, he is there all the time. He belongs to nitrogen. He was born with nitrogen and he's going to die with nitrogen. But what about this hydrogen electron here? This electron is shared between these 2, isn't it? So it spends time here and time here. But because the change in electronegativity is equal to 0.9, what is it saying? It's saying that it's not equally shared. It means that the nitrogen gets a few spins to 1, a few spins to 1. So this side, the nitrogen side here, all right, has got more of the electron, which means this bottom side is slightly positive, isn't it? Hence where the hydrogen bond comes in, isn't it? What happens now then? What happens now is that because it means that this side is a little bit positive every now and again, because the electron comes, then it's neutral, goes back, then it becomes positive. It's an unequal sharing, which means that essentially, and once again, hypothetically, this side might only be a minus 0.5, 0.7. But can you see you've got a -2? This isn't as strong because the electron's not there all the time. It's being shared out with the hydrogen, okay? Which means that the lone pair can exert more force and push the other 3 legs down more than they would if it was equally shared. Okay, I hope that sort of cleared up that bit. In the next one, I'm going to look at quite a lot. We're going to go through the entire hydrogen nitrogen cycle with making ammonia. We're going to look at the stoichiometry, we're going to look at the bond breaking, the enthalpy, entropy situations, and we're going to go through that because that covers, in one question, covers most of the bits and pieces of the syllabus in one. So I'm going to try and get through that, and it's possibly going to be a bit longer than normal.